function is entitled their derivative. This is basically what we're going to be doing for the rest of their calculus sequence. We're going to be talking about how to find derivative of functions. First, let me try to explain to you what a derivative is. If you have the function f of x is equal to x squared, that function looks like this. X and y. And I'm going to tell you what the derivative is. The derivative is 2x. That is, the derivative of f of x is 2x. And it's denoted by f prime of x. That means the derivative of x. Now, what does the derivative give you? It gives you the slopes of tangent lines. Maybe first we should have talked about tangent lines. Well, if you have, say, this function, around this x value, I want to draw a line that only crosses the graph in one place. At this point, I want to draw a line so that around that point, this tangent line touches in one spot and one spot only. And here is the tangent line. Just for the record, it's going to cross this curve. It's going to cross this curve out here eventually. And, maybe this curve could have gone like that. That probably would have been easier. But nonetheless, around this x value, this line crosses the curve in one point, namely that point. If we talked about this point here, this would be the tangent line. This point here, this here would be the tangent line. But notice, around this point, it only touched right there. It touched the graph there, but that's far away. Now, what does far away mean? Far away can be very close, actually. Okay, let me try again to erase this, and I'll show you that it can be really close where it crosses. For example, if you have this curve, and I'm interested on right here. Well, that's the tangent line. But now I can make it a little bit shorter. That's still the tangent line. Around the points of interest, around that point, it's not really, it's only touching in one spot. But it can start touching right away. But, well, not exactly right away, but I think you know what I mean. If you have a graph that keeps going like that, well then, where it crosses, where the tangent line crosses the graph, can be relatively close. But really close to that point, it only touches in one spot. Okay, I hope that was understood. Hope I did a good job explaining that. Okay, so now let's go back to our function to the left. Don't worry what I'm doing now. I told you here's the graph y equals x squared, or f of x equals x squared, and I told you here is the derivative. Now, like I said, the slopes, the derivative gives you the slopes. For example, when x is 1, plug 1 in. 2 times 1 is 2. That is, at this point, this slope is 2. That is, f prime at that x value is 1, is 2. F prime of 1 is 2. If you now go out to 3, the slope of the, so this curve goes up higher, the slope of the tangent line right there. Just plug in 3 into the slope formula, which is the derivative, and 2 times 3 is 6. That is, the derivative at 3 is 6. If you come here to negative 2, what is the slope of this tangent line? Well, it's whatever f prime of -2 is. So I go to the f prime rule and I plug in -2 for x, and I get -4. The slope of this line is -4. And since I wrote so much, let me do this one in red. If I go to 0, this here is the tangent line, I hope, and the slope is going to be f prime of this x value right here, which is 0, and 2 times 0 is 0, which makes sense because the slope of a horizontal line is really 0. The derivative gives you the slope at a point of the tangent line. The derivative gives you the slope of our function. Okay, let me say that again. The derivative gives you the slope of the tangent line of our function at some point. Here is some function. Here is some point. The derivative tells you the slope of that line. Okay. Now, let's see what's going on. So now I just told you if f of x is x squared, then f prime of x is 2x. We need a way to get that formula on our own. And rather than giving you some formula, we're going to derive it. Okay, and we're going to derive it by looking at a series of pictures. The same picture, actually. Here are some curves. And I'm telling you the name of the curve. It's f of x. And I want to know the slope of the tangent line right here. Okay, that is, I want to know the slope of the tangent line at x. Now, I pick an x value far away. That is, I go to the right delta x. Remember, this is 3, and you go to the right 7. The number here is going to be whatever 3 plus 7 is. That is, it's going to be, actually, I'm going to go further. I'm going to go here. It's going to be x plus delta x. I don't know if I've already said it, but I'm going to the right delta x. Let me try that again. I'm going to a right delta x. So now, we have this point up here. Now, the tangent line, I hope it's clear to you what it should be. It should be that line there. Or the slope is, yeah, that's the tangent line. But we're going to approximate it with this line, which I hope you will say, that's not a good approximation. And you're right. That's not a good approximation. But nonetheless, for now we're going to say we're going to use that. So I'm going to make my right triangle. Here's my right triangle, and it has that hypotenuse, and we want to find the slope of that line. Well, since this is x right here, this y value straight across would be called f of x. And since this x value is x plus delta x, I go up to my graph, which is right here. I go straight across, and this here is going to be f of this x value, x plus delta x. Okay. So let us try to find the slope of that line, which has a special name. It's called the secant line. If you take 2 points on a curve, on a graph, and you draw the line, the straight line between them, it's called the secant line. We could have called it a Harvey line, but we called it secant. Now, this distance is f of x plus delta x minus f of x. For example, from 2 to 10, if you wanted to know how long that is, you subtract. You do top minus bottom. Okay, but that's exactly what I'm going to do. That's exactly what I'm going to do to find that vertical distance. But first, I'm going to make a comment about that vertical make a very, hopefully, obvious comment. This vertical distance is the same as this vertical distance. We'll call it the change in y. But nonetheless, it's f of x plus delta x minus f of x. And remember, this distance, I said it was delta x, but if you don't believe it, if you go from 2 to 7, how long is this? It's the right number minus the left number. It's 7 minus 2. It's x plus delta x plus delta x minus x. I'll take away x. It's delta x. But this distance is the same as this distance in the triangle. That's delta x. Okay? So the slope of the secant line is the change in y over the change in x, like any slope. That is, it's f of x plus delta x minus f of x over delta x. For like I said, this slope, the slope of the secant line, is not a good approximation to the slope of the tangent line. And the reason is delta x was too big. Delta x was too big. So now, to the best of my ability, let me try to draw the exact same graph again. Try my best to draw the same exact graph. And here it is. I'm going to pick the same x value. That is, I want to know, actually the x value is probably here. I want to know the slope of this tangent line. So we're not using the x value that I started to cross out. Alright. So now this time, instead of delta x being that big, I'm going to make it smaller. I'm going to let delta x only come out. I'm only going to use this distance for delta x. So this mark is x plus delta x. And I don't see the graph well, so I need to redraw it. And there's the graph. Alright, so now I have this point and I have this point. I'm going to approximate the slope of the tangent line with that line. I'm going to approximate the slope of the tangent line with this line. And it's looking better, but it's still not that good. Well, let us make a right triangle. Let us go straight across, straight up, and find the slope of our secant line. This is delta y, and this is delta x. But the same argument as before. When I look across from this point, I'm going to get f of x. And when I look across from this point right here, from this point, I'm going to get f of that x value, which is x plus delta x. Okay. So the slope of this secant line is the change in y over the change in x. But the change in y, that is this distance, it's the same as this distance, which is f of x plus delta x minus f of x. It's f of x plus delta x minus f of x, and it's all divided by delta x. But again, that wasn't such a good approximation. So what we're going to do is, in this area right here, we're going to do it all over again. That is, I'm going to draw the same graph to the best of my ability. I'm going to pick the same x value. But this time, I'm going to let delta x not only be smaller, but real small. I'm going to let delta x be very small. Right there is x plus delta x. Because I only went a little bit to the right of x. Delta x is really small. So you have this point, that's right above x. And right above x plus delta x, you have that point. Now, when I draw the line that connects the 2 points, it's very, very close to what the tangent line should be at that point. And we're going to get the same formula. The slope of the secant line is going to be this formula here. It's going to be f of x plus delta x minus f of x, and all of it gets divided by delta x. So what am I saying is the derivative? As if delta x gets smaller and smaller and smaller and smaller and smaller and even smaller than that, that secant line gets close to the derivative. So we have f of x plus delta x minus f of x over delta x. Now there's a reason why we learn limits, and here's the reason. We learn limits for one reason. So now I can say, you know what? I'm going to take this. By the way, this whole thing has a name. Not just f of x. Everything in the big brackets. This is called the difference. Can't be difference quotient. Difference quotient or difference function. Probably quotient. Okay, so maybe my name's wrong. But if we let delta x go to 0, then we get exactly the derivative. The smaller delta x is, here's x. If I pick a point far away, which says to me that delta x is this amount, the slope of the tangent line is not very close to the slope of the secant line. This is the slope of the secant line. It's not very close to the tangent line. If I let delta x be smaller, that is, I pick a closer point, now delta x is in between these two marks. It used to be in between here and here. Now I made it smaller. It's no longer way out there. Delta x is now just this distance. It's just this distance. And this secant line, although it isn't perfectly close to our tangent line, it improved. And if I pick an even smaller, a closer point, that means I'm going between here and here. So my delta x is smaller. I'm going between these two x values. Well, if you draw this line is closer to this line. And if I keep letting the point out here get closer and closer to the initial point, then delta x is going to 0. And this here has meaning to us because we know how to take limits. Now I'm defining this to be the f prime of x, which means derivative. So that's how we got the definition derivative. I'm going to cut the tape here. Okay, well, actually, we're going to derive the alternate definition as well. And then in the next case, we'll use their definitions, the two definitions. So right now we have that f prime of x is equal to the limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x. Okay. Now, how do I want to do this? Let's see if I can do this. If I let delta x become c minus x, I'm going to say delta x is c minus x. So, f prime of x is equal to the limit. Now, if delta x is going to 0, and this is delta x, that means x must be getting close to the c. C is a constant. If this is going to get close to 0, then x must be getting close to c. And we have that delta x is c minus x, and we have x is x. So when I add these on the left side, I get x plus delta x, which is exactly this. And on the right side, the x's cancel out, and I get c. So this becomes f for c minus f of x. And in the denominator, I have delta x, which I clearly said was c minus x. And I'm going to do one last thing. I'm going to multiply the top and bottom by negative 1. Remember, if you have a minus b, and you multiply by negative 1, negative 1 times negative b is b times, and then negative 1 times a is negative a. That is, if you have a minus b and you multiply by negative 1, you get it in reverse order, b minus a. So, I have one thing minus another. If I multiply it by negative 1, I switch to order. And if I multiply the top by negative 1, I have to multiply the bottom by negative 1. Here is what's called the alternate derivative formula. The alternate derivative formula. Right here. This is, excuse me, it's right here. This here is the alternate derivative formula. That's the alternate derivative formula. Now, if you wanted to, you can argue from the grafting viewpoint to get that same formula. I just gave an algebraic proof of how you can derive the alternate. I just want to think for a moment. I do have one typo, excuse me, a major typo. My major typo is right here. Sorry, it's not f prime of x, but rather f prime of c. It should be f prime of c. Do I have that error anywhere else? It doesn't look like it. Okay, it's f prime of c. Now, let's show you why that's true. Okay. Now, let us look at f of x minus f for c over x minus c. So, you have some curve, and here c. So across here, you're going to have f for c. And then over here, maybe, you pick x, and across here, you naturally are going to have f of x. Now, I'm going to approximate the tangent at c with this one. Well, the slope of this secant line is going to be the change in y over the change in x. It's going to be this change over this change. For this change is the same as this change, which is f of x minus f for c. And the change in x is just the change in x. No, the change in x is x minus c. It's x minus c. So the slope of the secant line is the change in x, which is f of x minus f for c, over the change in x, which is x minus c. And if we let x get closer to c, if instead of picking x right out here, well, actually, maybe the x we chose was really there. Why? Because when you look straight up, you get the point that I said you get. If you look straight up, that's where you get f of x. Well, if I let x be closer to c, if I pick x right here, then I go up to this point, and I use this as the secant line. But that's very close to their actual tangent line. That is, if I let x go to c, if I write the limit as x goes to c, I get the derivative exactly at c. And that did not come out. I get the derivative at c. Okay, so we have the regular derivative, which I derived. We have the alternate derivative, which I derived two different ways. And next section, or next video, we'll talk about how to calculate derivatives or functions using the definitions and the alternate definition.